Hello, Mr. Vessel here today, and we are going to be continuing to look at some AP statistics free response questions. The question we're going to look at today is from 2004, and this one is about doing a significance test with two different proportions. And there's lots of different to make in order to do this problem successfully. So we're going to talk about those things. We're also going to talk about some other options that you have as you work through this task, and let's dive in. So, this one starts out about tumbleweed, commonly found in the western United States. It's a dried structure of certain plants that are blown by the wind. Kochia, a type of plant that turns into tumbleweed at the end of the summer, is a problem for farmers because it takes nutrients away from soil that would otherwise go to more beneficial plants. Scientists are concerned that Kochia plants are becoming resistant to the most commonly used herbicide, glyphosate. In 2014, 19.76% of 61 randomly selected Kochia plants were resistant to glyphosate. In 2017, 38.5% of 52 randomly selected Kochia plants were resistant to glyphosate. Do the data provide statistical convincing evidence at the level of alpha equals 0.05 that there has been an increase in the proportion of all Kochia plants that are resistant to glyphosate? So, a couple things that we want to make sure that we pay attention to. Like, every AP exam is going to have a task where you have to do a full hypothesis test or a confidence interval. And when you see the phrasing, do the data provide statistical convincing evidence, this is phrasing that you need to either be doing a hypothesis test or a confidence interval. Typically, it's a hypothesis test. And we're going to do a hypothesis test here. We even get the alpha level that we're going to test it with. So there's a few things that you got to make sure you do. The first thing that I'd like to set up is really just the null and alternative hypothesis. So in this case, we'll notice that the thought is that there's an increase in the proportion of Kochia plants that are resistant. So what we're going to do is set up our alternative hypothesis that way. So the null hypothesis is going to be something like the 2014 and the 2017 versions. What we're going to assume is that these two things are the same, and that's true for all hypothesis testing. So we're going to start with the proportion of 2014 equaling 2017's proportion. But we have to define these. We can't just leave it like this. This isn't sufficient to describe what the proportion is. This doesn't say if it's the proportion that are resistant or not resistant or what. So we have to be specific in how we define these. So we're going to do that here. What I want to represent P for 2014, this is the proportion, and I should even write the word true proportion. The true proportion of plants resistant to glyphosate in 2014. And the 2017, this represents the true proportion of plants resistant to glyphosate in 2017. And it's really important to mention the word true here. Like, we're doing a hypothesis test, and it's about the true proportions. It's not about the samples. So we use the samples to see if this hypothesis is true, if these two samples are close enough, and if they are close enough, we'll be able to claim that these two proportions, the true proportions, are also equal. And the alternative hypothesis, this is the one that maybe is the belief in this case, and in this case they want to know if there's been an increase in the proportion of all Kochia plants that are resistant to glyphosate. So as if I keep the same similar notation here, what we're trying to see is if there's now an increase, which would make 2014 less than 2017. So what we're going to test is really using our samples, like, is this true now, based on what we collected for our data in the previous years. And now I want to mention there's lots of correct ways to set up your alternative hypothesis and your null hypothesis, but it's got to be something. What's important about it is that you have to define what your parameters are, and you have to have some correct version of this. Like we could easily flip the 2017 and 14 around as long as we make the symbol greater than. Another version of this, and sometimes this is kind of nice too. This is what we're going to use in the formula here, but it could also do something like this. The proportion of 2014 minus the proportion of 2017. The null is that it equals 0. The reason that this is kind of nice is that we can use this in our formulas in just a few minutes here. The other version, proportion of 2014 minus the proportion of 2017 is less than 0. So for our alternative hypothesis, we're going to see a less than test here. So we're going to have a left tail test. And then the equal sign to 0 here is kind of nice, again, just because it's going to work out really well with the formula here in just a few minutes. But before we do get to that formula, we want to make sure that we have to name the test and then check our conditions for the test. So what we're going to try to perform here, as long as our conditions are met, is we'll use the 2 proportion, let me say it this way, a 2 sample z-test for a difference of proportions. And we can do this with either the words or the formula. I'm going to do both, actually. So the formula looks something like this. We're going to have a z-score here. And in order to calculate our z-score, what we're going to use is the proportion from 2014. And we're going to subtract the proportion from 2017. And we also have the assumption from our null hypothesis that the proportion from 2014 minus the proportion of 2017. This is going to be 0 in just a few minutes. And then that's our numerator. The whole denominator is going to be our standard deviation of the sampling distribution of these two proportions. And this is where there is some choice here. You can do a pooling technique. You can actually do a non-pooling technique. I think most students prefer the non-pooled version of this, so I'm going to stick with the non-pooled version as well. Basically, the reason that can be advantageous, you're going to use the same fractions and same proportions throughout the whole process here. So this sample proportion from 2014 is also going to be part of the standard deviation. And we just got to remember we're going to add variances here. So our formula is going to look like this. The proportion from 2014, 1 minus the proportion from 2014, all over the sample size from 2014. And also going to have to add up, this is adding the variances here, so that this part on its own is just the standard deviation of the sampling distribution from 2014. And we're going to do the same thing with 2017. So we use that sample, 1 minus that sample, and divide by this sample size from that year. So all of this will be what we'll use to calculate our statistic in just a minute. But again, before we do this test, we actually have to show the grader that we know what the conditions are to do this test. There's 3 things that we need to be able to either check for or safely assume, and we can't just use a checklist. We actually need to make sure that we show how we know that these things are met. So the conditions that we need to make sure is that that we've got some random samples. So one of them is that we took, and it says it up here, we can notice it, here we go, 61 randomly selected cochia plants were resistant to glyphosate, and then we have a success rate in this particular case. And then we had another random sample. So first thing I want to mention is that these were random samples. Random samples in each year were taken. And another thing that we have to be able to assume is that these samples are independent of each other. I think that's a pretty safe assumption. The 2014 and 2017 samples here would be independent of each other. These random samples are safe to assume independence here, since they were in different years. We have to make sure that our population is large enough and that our sample is also appropriately sized for making sure that we can assume that this is a normal, approximately normal sampling distribution. So to do that, we're going to make sure that we have at least 10 in each of our groups. So I like to usually make a little table for these. We have, let's see, we need at least 10 in each of the following groups. There's basically a couple things that could happen when we go grab a sample. We have the 2014, and we have the 2017 sample. And then what we measured was whether it's resistant or not resistant. I'll use resist or not resist. And all I want to make sure that I show here is that I've just got a large enough sample. So we were told that there were 61 samples taken in 2014, and we were also told that there were 52 taken in 2017, and that's fine, but what we have to make sure is that the numbers within this chart, that this number and this number, how this 61 was comprised, these are both bigger than 10. So if we have too small of a sample, we wouldn't be able to assume that these are normal here. So in order to check these, we were told that the n from 2014 and then our p hat from 2014, we have these numbers. We have 61 and we have 0.197. So all we have to check is what is 61 times 0.197, and it's a little bit bigger than 12. Looks like it must have been 12 when we made this calculation. We'll put approximately 12 here. So we have 12 resistant plants to in 2014, which must have meant we would have had 49 that were non-resistant. And we're going to do the same thing for 2017. So n from 2017 comes a probability that they were resistant from 2017, and we can get a sample size here of number of, I guess you call them successes, resistant to glyphosate. So we had 52 with a 38.5% resistant rate. So we're going to multiply those two numbers together, and we get a number that is just above 20. So it must have had 20 plants that were resistant, which must mean there were 32 that were not. And what we have to make sure is that we've got those met in this case, and we've shown the number of resistant and non-resistant plants. They're all greater than 10. But again, it's more than just checking a list and just saying, oh, we have to show the actual successes and failures in each of these groups here. So these are all large enough, so that condition is met. And then we have one more thing that we should check, and that's that it comes from a large population. So the last thing we need to make sure, it's another safe assumption here. It's a large population, and that's met because it's safe to assume we have to make sure that it's at least 10 times our sample. So the population, it's safe because safe to assume there are more than 10 times n for the population. So basically all you need to be able to assume the population is greater than 610 for 2014, and the population would need to be greater than 520 for 2017, and both of these are safe to assume here. We could assume there's millions of these plants every single year, so it's a large population, and it's going to be okay to use that 2-sample z-test and then look this number up here. So we're finally ready to do our calculations, and I want to leave this formula up as I kind of fill in some of these things here. So we've got the formula, we've checked our conditions, we've got our hypothesis, we're finally ready to calculate our z-score. So what we're going to do is plug in some values here. So the proportion from 2014, that was 0.197, and the proportion from 2017, 0.385. Remember our null hypothesis, if the assumption is that these two things are equal, then we're going to assume that when we subtract these two, well, we don't have to assume, when we subtract these two things, then that number will be 0. So that's one of the big keys with any two sample test, whether it's a mean or a proportion. You will end up having a null hypothesis effect here, where you're going to get 0 for this parameter subtraction, for this parameter difference. And then we're going to take the square root of this whole thing here. We're going to use 0.197, 1 minus 0.197 over 61 plus 0.385, 1 minus 0.385 over 52. Now I do want to mention, like, it is possible to do this in another way. It is possible to pool. Pooling works in a way that it's, instead of looking at both of these samples separately and combining their variances, it's kind of an average of the two. So instead of using the 19.7% and the 38.5%, you basically weight average these values, and then you can use that value as your sample proportion for the combined samples. And that works perfectly fine. The non-pooled works perfectly fine. Again, I prefer this. I think students prefer this because of the repetition of the same statistics. So, and as far as like the results, you're not going to get a different number. Like the pooling version of the z-score and the non-pooled version of the z-score, they're typically going to be within 100th or even a 1,000th of a decimal. So you're not going to get a different result by pooling or unpooling. It's kind of an option that you get to choose. So I think we're ready to put this thing in. I'm going to type this thing all in at once here. So I want to make sure I use some fraction that makes it look a little nicer. 0.197 minus 0.385, square root, another fraction, 0.197, 1 minus 0.197 over 61 plus 5. Oops, forgot the 8 over 52. Make sure that looks good. And I get this z-score, 2.22. And one thing you might notice, my z-score is negative, and that's totally dependent on how I chose to set up my original hypothesis. Had I flipped it and made the 0.385 first, and I could have gone down at my null and my alternative. If I would have said 2017, the proportion of the 2017 true proportion is greater than the proportion from the 2014 plants, then I'd end up with the same number, but it'd be positive. Either way is going to work perfectly fine. And one thing I do like to do with these things is sort of illustrate what we just did, where the assumption, our null hypothesis is 0, comes from the fact that we're going to assume that these two things are 0, that they're equal to each other. And we go out, we grab our sample, and our sample difference, well, I didn't actually just calculate the numerator on its own, 0.197 minus 0.385. You see there's a difference of almost 19%. What we just calculated was that, I'll put it over here, p hat from 2014 minus p hat from 2017, that number is negative 0.188. So we just calculated a sample difference of almost 19%, and the z-score for this calculation is negative 2.22. And what we're going to do is we're going to look this number up and see if it falls in the critical region. So get our z-table. Could also use a calculator for this part, but I thought use a table would be perfectly good too. So what we have here, got our standard normal probability table here, and our z-score just came out to be negative 2.22. So here we go, negative 2.22 is 0.132. So what that number means, this number that's a little over 1%, this is the probability that our sample differences is almost 19% if they're supposed to be 0. If these two things are actually equal, the probability that our sample occurring would happen about 1% of the time, 1.32% of the time. So this is significant at the, and remember it told us to use alpha of 0.05. So alpha was 0.05, and just as another way to attack this, if I were to set the alpha up at 0.05, there is a key number over here somewhere that would cause us to reject the null. There's just this point over here to the left that we're like, okay, this is just way too low for us to say that these two things are equal still. And that point has been met here. We're over a little bit further to the left. Our probability is about 1%. We were taking 0.5 or 5% to be the cutoff point. So we do have evidence to reject the null here. So anything on this side, let me put it this way, this is the reject the null region, and we meet that here, so we're going to reject the null. This side is failed to reject the null. Anything on this side of this pink X would have been failed to reject. We wouldn't have enough evidence if my sample would have come out on this side. With my z-score and my p-value calculated, I now have my alpha. We're ready to make a conclusion, and I'm going to say something like this. This sample provides evidence to reject the null. Oops, forgot the word evidence. Evidence to reject the null hypothesis. And I've already got, I'm going to say y, but I've already got my p-value. This is p. And I've got my alpha. And if those two things are on my paper, I really don't need to restate them, but I'm going to. Because p, which is 0.0132, is less than alpha, which is 0.05. And this is fine. It's a good start. I tend to do my conclusions in a couple of sentences. One that just sort of makes the decision if I'm going to reject or not reject the null based on some sort of calculation that we made. But then two, we got to get it back in context. So we have to get this into the situation and what it means. In this particular case, remember our null and alternative. If we reject this null, what we're saying is this is more likely to be true. So I'm going to write this in a context now. Just something about that we have evidence that the proportion from 2014, maybe I should have, I was going to write less than. I think in mid-sentence here, I'm going to flip my mind here. It says, remember the prompt, is there evidence that there's been an increase? I'm just going to reword it to that way instead of saying that it's lower. So we do have evidence that the 2017 proportion is greater than what it was in 2014. Now, the P of 2017, that is defined already. That's the true proportion of plants resistant. So we have evidence, remember this is the true proportion of resistant plants. To glyphosate. So that has now gone up And that's what we wanted to make sure that we could show. So there's a few pieces. Again, as a summary, in order to do this task, we have to do a few things. We've got to make sure that we make a null and alternative, that we define those parameters. We've got to name the test. And we can name the test with either. I really recommend both. The formula is going to come in handy too in a minute. But then we have to check these conditions. So there's a few things you got to check to make sure you can do this. And then when we actually get to the point where you calculate it, we got to get that z-score, find that p-value, and then we got to make our conclusion based off the alpha level. And sometimes we get to choose this number, sometimes we don't. And this case, we were told what to use. So that was the 2019 problem number 4. And again, it was kind of a big one. It had to do with 2-prop z-test. Hopefully you found that helpful, and thanks for checking it out.